Okay, I think we can start. Jochen, thank you. Please introduce yourself and the subject.
Yeah, my name is Jochen Hoenicke, and I come from the SMT solving area. So I wrote my own SMT solver, and I started with Setora last year. And in this talk, we will look into, this will be an advanced webinar, and we will look how we can use quantifiers in Setora specification to prove more complicated programs. So I wanted to start with a simple example. This is kind of motivating example for quantifiers. And this example comes from OpenZeppelin. It's in so-called EnumerableSet, which is a mixture or a combination of an unordered set and an array. And so the set is implemented by a map. You can see the data structure here on the left-hand side. So we have a map that maps every element to some value, and this basically maps from the elements in the set to some value that indicates that the element is in the set. And there's another view on the same data structure, namely the values, where we list all the values in some order as an array, so we can access also the elements in the sets very quickly. So we have many operations that are in constant time, so we can add new elements to the set in constant time, we can remove them, and we can check for containment without iterating a list. We just use the map for this. And we can also enumerate all the values. So we have another view on the same elements where we have the values. And yeah, this implementation comes from OpenZeppelin. And if we want to verify it, then yeah, we can look at the example. Here's this EnumerableSet file. It's a library. So you need to write another contract that uses the set. So this just is a very simple contract with a few functions for each of the operations in the set, and they are public so that we can test them in our Setora solver. So what we then write is a specification, and the simple specification would be, we add these functions. All these functions are environment free. This helps us because we don't have to reason about block number or message sender. We can just ignore the environment and just call these functions. And this only works if the functions are environment free, then we can mark them as n-free. And in this case, they are. And then we write a rule for every function. For example, we want to prove that if we add an element that in the precondition we require it's not contained already in the set, and we add it to the set, then the call shouldn't revert. And also the value should be added to the list, so to the set, so it should now be contained and the result should be true. And also no other value should be added or removed. And this we can express by just guessing another value. We require that it's different from the value that we add. We remember if it was contained before. And then we compare call contains afterwards and compare if this gives the same result. And yeah, similar, we can write all the specifications for the other functions. And if we run the specification, I've already done this today, then we will notice that many of the functions fail. And the reason why they fail is because the Setora prover will consider any possible starting state. So it will assume you start with any storage, and it may even start with a storage that doesn't correspond to a well-formed set. So for example, if we look and remove success, then we get the error that remove should never revert, but it reverted. And if we look into what happens, we see that there is in the storage some element D at some index 705, and I think we removed this element here. Yes, we removed the element D, and this call reverts because well, it wants to remove the element at position 0x705, but the array is not so big. So this index doesn't point into the array as we expected. And this is because we start in any possible state. And to fix this, we need to tell the setter approver which are the states that the program should start in, that the contract can start in. And this seems a bit more work, but the advantage is that we will find more bugs because we will consider any possible starting solution. So we don't need to, we will find deep bugs that only happen after many function calls. And we also verify that the invariant, if we give an invariant, we also verify that every function will fulfill the invariant. So if we say that somehow a correctness criteria that the two different views are always in sync, then it will verify for every function that this is really the case. So what is the correctness criterion here? So we have two views, the index view and the values view, and we want to say that they correspond to each other. So the indexes view contains, for every element in the set, it contains the index where it appears in the value array. And there's a +1 here because index 0 means that the value is not in the set. So the 1 here means it's a zeros element. So here the first element in the value set is the 0x23341 and so on. And we can do this, specify this with quantifiers by saying that for all elements, these indexes and these values match. And for this, we can use two quantifiers. These formulas may look a bit scary, but they are not so difficult. So this A means for all. And so we say for all indices I, if the index is an index into the values array, so it's smaller than values length, and it's greater or equal 0, then this equality should hold, namely that if we read the value at this position, so for example, we read the value at position 0, we get 0x23341, and we then reference it with the indexes array, then we get the index +1, because we always get 1 in the indexes array. And similar, we have the second invariant that does the reverse direction. So if there is some element here in the indexes array that is not 0, for example, this 0x11123, then it should contain a value that is smaller or equal than the length of the array. So equal because now the index is +1 of the index that it should be. And so we also need to subtract 1 from the index and then look into the values array. And then we should find the same value v again that we had here in the beginning. So are there questions so far? If not, I continue. So we could already, before we had quantifiers, we could already specify invariants that range over all elements. And the way it worked before was we make an invariant and give it a parameter. So we can make an index invariant that takes as parameter the index, and then we have basically here the formula that was under the quantifier on the slide before. So we say if index is smaller than values length, then yeah, it should be this equality should hold, and similar for the value invariant. And if we do this, we can also verify this contract. The problem here is that basically the user has to do more work. So if we want, for example, to verify the remove function, we need to know how the code works. We need to know that the remove function only works if the values invariant holds for the value that we want to remove. And this is something you may have guessed. But the second more surprising thing is we also need to know that the index invariant holds for the last element in the values array. And to understand this, you need to know how remove works. It works by moving the last element to the position of the deleted element, so that it will so that the array will not have any gaps in between. And therefore, it also needs an index variant for values length -1. And this is something that you have to find out, that you need to add this index invariant. And you may figure it out if you look at the counter example and see that there was this assignment of this element and there was something wrong with this. But yeah, you still have to do manual work. And the other thing is you also need to figure out here what the preserved block is. And this is similarly complicated. So for example, if the remove function is called, we need to say that the remove function, to show that the index invariant holds afterwards, we need that the index invariant holds before for the same value, but also that if we call remove, that the index invariant for the last value in the array holds. And figuring out all these invariants is quite tricky. So what we can now do is we can use universal quantifier and can make one invariant with a universal quantifier and let the prover figure out all the instances of this invariant that we need. So instead of requiring the correct invariance, we just require the one invariant, the index value invariant, which is basically the both invariant that we had before and with a universal quantifier. Yeah, and so this is how we can do it. And the other advantage, we don't need a preserved block anymore. So this invariant is already inductive. So it means if it holds before and we call, for example, the remove function, then the prover itself can prove that it holds afterwards. We don't need give any other hint to the prover. And we also only need to require the invariant, and the prover figures out the instances that we need. So there are some limitations with these quantifiers, and yeah, I have to mention this because if you start using these quantifiers, you will notice them. And the first and most important thing is the quantified formula can't invoke solidity view functions, which is somewhat expected. So you can't say for all x and then call a solidity function. Doesn't, even if it's just a view function, it's not clear what should this even mean. And the other thing is you can't access storage inside quantifiers. And basically the way we accessed storage before was using these view functions. And since you can't use view functions, you can't access the storage. So this is one limitation. And the other is that the prover may not find all necessary instances. So let's first look at the first thing, because this is very severe. So yeah, we can't access the storage and the view functions cannot be called, so we can't make the usual workaround and use the view functions. So what we can do is we can use a ghost copy. So we can add to our specification arbitrary ghost state. And this ghost state is like similar to the storage of a contract, but it's only visible by the spec. and it's visible by the spec. So you can use it in quantifiers and you can use it everywhere in your spec. And this ghost code is not visible by the original code. So you can never break your original code by adding ghost state. This is also something neat. Our philosophy is we add a specification separately from the code, and we don't touch the code that we want to verify. So we need to make sure that the ghost copy of our variables contain the same thing as the storage variable themselves. And for this, we can use hooks. And hooks are a mechanism to be notified in the spec whenever a value on the storage changes. So if someone writes to the storage, and you can even use it when someone reads from the storage. And here we add one ghost variable indexes, which corresponds to the indexes array that we have, or the indexes map that we have in the Solidity code. And this is here a simple mapping from, with the same key value range and the same value range. So it maps bytes 32 to the indices. And we can make sure that it initially contains only 0 by this init state axiom. We say for all x it's 0. And then we need to add these two hooks. One is the store hook. This is called whenever the variable indexes, which is a variable which lives in the structure inner, which lives in the structure set, which lives in the current contract. Whenever this map is changed, we want to be notified. And we also get the value, so the index at which the key of this mapping, which was changed, and we get the new index that was written into this map. And what we can do in this, what we do in the hook is just we store the same new index into our go state. So now underscore indexes and the indexes in our go state are always in sync. The other thing is we need to tell the prover that they are always in sync. So we also need a load hook, and this makes sure that the prover knows that whenever we read the storage, we read the same thing as the ghost state. And you can basically make these hooks, you can write them automatically. So we don't have a tool yet that would enable this for you, but it's not difficult to write these hooks. You can, it's a very mechanical task. And after you wrote this hook, you can use the go state in your quantifiers. The other problem with quantifiers is that we need to, that the prover only has heuristic instantiations, and it may not be sufficient. So for example, if we have some quantified formula that states that, yes, AI is smaller equal AI plus 1, so the array A is sorted, then with this quantifier, you could in principle prove that A0 is smaller equal than A100. But if you want to prove it, you need a lot of instances. You need to, the instance that A0 is smaller equal A1, A1 is smaller equal A2, and so on. And since this would not yield into a good query for the SMT solvers, so if we would do this, we would always get timeouts. We have a heuristic instantiation that will only add a few of these instances. I think it will only add the instances that contain A0 and A100. So it will contain A99 is smaller equal A100 and A0 is smaller equal A1, but not the other instances. And so with our heuristic instantiation, we can't prove it. You will get a counterexample, and the counterexample is basically slightly wrong. But there's an easy way to fix it. because you can use this formula instead. This is equivalent to the first formula. It also states that the array A is sorted. And it allows you to prove the same property with just one instantiation. And our heuristic will find this instantiation. So sometimes if it cannot prove your quantifiers, you can try to think about, can you help the proof by formulating the quantifier in a different way? The other thing is that the instantiation heuristic is based on searching values that build existing terms. And what this means is we have, assume we have this quantifier, then we want to instantiate it in such a way there was a question in the chat. So this formula allows that I and j are the same. Yes, this is true, but actually it's not important, because if I is equal to j, then ai is equal to aj, so they are equal. So this is always true if I is equal to j, because the right-hand side is equal. And by the way, if it's strictly sorted, then you can't do this trick. But this is a known problem. Yeah, so so what we want to find here is an instance. So for example, our prover may read the array values at the index j. And so we want basically to instantiate this quantifier such that I minus 1 is equal to j. So the useful instance would be I is equal j plus 1. And this is kind of solving a formula. And this may even get more complicated if there are possible overflows. So if this is not a math int, but a uint 256, then you have to check that j plus 1 doesn't overflow, or if it overflows, it will also overflow if you do I minus 1 here. And it will basically cancel itself out. And we decided to ignore or to not do this and just say, don't use a quantifier like this. It gets even more complicated if you do more strange things like 2 times I, for example, would mean that this property only holds for the even values of values, which is something that makes instantiation even more difficult. And or if you add here 2 variables I plus j and you quantify over I and j, then we are also we don't know which instance we should use. So our simple heuristic says we don't support this. Instead, please use the quantified variable directly as a function parameter or as an index to an array, because this is what we support. So what you can do is you can reformulate your quantifier and use the variable minus 1, so that I is now between 0 and values length, and then you can get rid of the minus 1 here, and you have a plus 1 here, and then it's easier for the solver. And now our heuristics works for this. Okay, so let's do a demo here. Yeah, I already wrote this specification. So here, this we have already seen. Here is are the ghost values that we added. So on the slides, I wrote values here. I called them ghost values to make more clear that these are ghost values. Then we have the hooks. These are the store hooks. Basically, we have a hook for the values array and for the indexes array. And there's another hook that is for the length of the values array. So we can also access the length of the values array. It needs a special offset 0 here. yeah, we can't. I think this is still a problem with CVL, that you can't make a hook on writing the length, but you can do it if you know that the length is stored at offset 0. And here are the corresponding read hooks, and the read hooks just require that the value that is read from the storage is the same that was written in the ghost state. And now we can state our invariant. So the invariance, yeah, this is the first invariant that says that if index is between 0 and ghost length, then the indices values is equal to index plus 1, and this is the other one with values, and we have already seen them on the slides. I think I used an implication before with not equal 0, but it's equivalent. We can also express that a value is in the set by looking at our ghost state. So if ghost indexes is not 0, we know that the value is in the set. And now we can basically write our rules as before. And in some cases, so for example, for remove success, we need to require the invariant, that this quantified invariant. So we can run this through the solver. It should take just a minute or two, but I have already done this because just to make sure that it's still working. And now we get all green. So with this invariant, everything works. And we can also try to basically break our code and see if we can find bugs in our specification. So this here, here's the EnumerableSet, and we could make some arbitrary mistake. For example, we put here not a value index -1, but a value index. So we forget to subtract the 1. And if we do this, then we need to run the setter approval again. Set configuration. So let's hope that it works. Yeah, it's now queued. So the way it works is that the prover run is queued on the server, and it waits for free resources. And as soon as it gets free resources, it starts running the job. And yeah, I mean, we can, yeah, I think we can wait a few seconds in the hope that it will appear. Hope the queue is not too long today. I think I ran it with a different bug before, but yeah, it's still queued. It takes longer than normal. Maybe we can look at another example in the meantime. So another example that we looked into is LinkedList, and we looked into the DoubleLinkedList from Morpho. And this is a data, yeah, linked list should be a known data structure. You have a pref pointer, a next pointer, and some value that you store for each account. And yeah, And this the list is basically a mapping from address to these accounts, and the pref and next pointer will point to the next address. By the way, the run is now working. So show it, hopefully. So it is already dumping out on the command line all the results. There is something violated, but the UI is not. Maybe wait. Yeah. So we have pref and next pointer. We have a head and tail of the list, and then we should build a doubly linked list, and then we have, for example, the remove function, which removes from the middle of the list, and then it updates the pref, the next pointer of the previous to point to the next, and the pref pointer of the next element to point to the previous account, so that it skips the current account and deletes this account, and we want to prove that this function is correct. So yeah, what we do is we write a specification for this, and this is the specification, and we do the same thing as before. So we add the go state for next and pref, we add the head and tail pointers, and we add the hooks. And then we need to build an invariant that basically states that pref and next points always points to each other. So yeah, first we need to say that the pref and next of head and tail point to the head and tail. That the next of the tail points to 0, and that the pref of the head points to 0. But this is only the case if head and tail are not 0. So if they are both 0, the list is empty. And we also need that for every address that pref and next point to each other, and there are also some exceptions again. So first, there are a lot of addresses which aren't allocated. And for all unallocated addresses, we want that they point to 0 and that the value is 0. And for all others, we require that the value is not 0, because the value is indicating that the element exists in the list. The address must also not be 0, so we need to state that the null pointer is never allocated. And we need to say that, if the address is a ghost head, its pref pointer is 0, or otherwise the next pointer of the pref pointer points back. And the same for the other direction, the pref pointer of the next pointer points back. And there's always the exception that this doesn't hold if it's the head or the tail. So it was quite a bit of a struggle to figure out these exceptions that you need, that you want to write that this holds, and then we see it doesn't even hold because it doesn't hold for the head and the tail, and then you'll have to figure out how to write these exceptions. But once you wrote it, this invariant can be verified automatically. So our prover basically runs every function on a state that fulfills the invariant and proves that after running the function, the invariant holds again. And this, this way we know that every reachable state will fulfill this invariant, and we can use it in our rules as a requirement. Yeah. So I also added some rules. For example, that if you insert an element, that you don't remove any old elements from the list. Yes. But yeah, I think we can go back to our example that we had previously. So we previously introduced a bug in our code, and now our set invariant, our invariant is no longer preserved. And if we look, why isn't it reserved? Well, we have the remove function, and this remove function violates the invariant in the post state. And we can even look into the details here. So we can see here it was assumed in the pre-state, the invariant. It was required in the post state, and then it evaluated false in the post state. And if you want to know why it evaluated to false, you can also look deeper into this. So we have basically the invariant has these true for all quantifiers. And for both, there is a counterexample. So for the first, the index is, if the index is 0x10f0, it's a counterexample. And for the other, we have this value that is a counterexample. And then you can try to figure out why this happened and also look into the remove function itself, which were the parameter it was called with. What happened here inside the remove function, what is the storage after the remove function was called. And this should help you to figure out why there is a bug in your code. So you can even see the values of the quantifiers now where your post condition is violated. So let's get back to the linked list. So I added this invariant, I added a few rules, and then we can run it. And since it always takes so much time until it gets queued, I have already done this before, and we see that all the invariants are preserved. So somewhere is the next brief match, this was the main invariant, and for every function that we can call in our contract, the invariant holds afterwards. So we know that everything is fine with this contract. So far, any questions? Otherwise, I will continue with a more advanced thing, namely when we have linked list and we have some function like insert, then we often want to say something like, after calling the function insert, the key is really in the list. And the way I did it before with the DoubleLinkedList was a bit of cheating. I just checked if the function that checks if it's inside the list returns true. And this function just looks if the value is not 0. So it doesn't check if it's really part of the linked list. It just checks if the value is not 0. And if you want to try to say that the value is not 0 for all elements in the list, you need to somehow express what does it even mean to be an element in the list. And this is kind of tricky. So here we have I reduced this example a bit to a singly linked list, just to make it easier for me to get to show only the important part. So we have a singly linked list, we have just one head, we have a next key, and then we have an insert after function. It requires something. It requires basically that the after key is valid and that the key is not already inside the list. And then it does operations and enqueues the key. So I have a diagram that shows how this insert after works. So we start with the linked list where the head points to the first element. The first element points to some elements in the third, and this element here, and this points to 0, which means this is the end of the list. And we now want to insert the key 0x23341, this one, after the key 0x1 and so on. And what we do is we first copy the next pointer of this field into this field, so that this new key that we insert points to the element that we pointed before, so that we don't lose the third element. And then we can update the next key of 0x1 and let it point to the key. And now our linked list is well formed again, and the new element was included in the list. And what we want to say is that it was included in the list. But how can we express that the key is in the list? And you may think to write something like this. So either the key is the head, or the key is the next key of the head, or the key is the next of the next of the head, and so on. But yeah, this has an and so on, so it's not a valid formula. And you can't even express it with a first order formula. So it's not first order expressible. This is this is a reflexive closure that we want to express, and it's well known that one cannot express it in first order. One would need higher order for this. However, we can do a trick, and the trick is usually to express it in higher order, you would say there exists some higher order predicate that expresses reachability, and it has the properties that the closure of the next key. And we can, instead of putting such an existential quantifier, we can just add a new ghost state for the reachable keys. So we add another ghost variable, which is called reach, and it takes now two addresses or 2 bytes, 32 as inputs. And it basically reached xy should indicate that there is a path from x to y of some length greater equal 0, just using next key. So the way this ghost state works is we initialize it first so that it has the right value. And the right value is that first every element can reach itself, because the path can have length 0. And also because the next keys are initially all 0, we also know that every element can reach the 0, the null terminator. And these are the only reachable elements. So this is a precise representation of the initial state. So we can initialize reach as above, and we can also update reach in the store hook. Whenever we update the next pointer, reach will change in some way, but we can express the way in which reach changes. And this is the first order formula, so we can even express it in our logic. And once we have this reach, we can then also use the reach in the specification. So how can we express the change of reach? There's this operation where we write the next pointer of some element A, and we insert the address of some element B in there. And this is a formula. It looks a bit scary, but it's not so difficult to understand. So this is a universal quantified formula because this reach may change at more than one positions, and we basically change it at odd positions, and we compute the new value of reachability from the old value of reachability. So the new value is here marked with at new, the old value with at old. And then we say that the new value, that x is reachable from y if it was reachable before, and it was not disturbed by changing this pointer, which means either a isn't even reachable from x, then y should still be reachable from x, and the other possibility is y comes before a. So if a is reachable from y, then we know y comes before a, and so then it's also okay, and it's still reachable. And the other possibility is that x can reach a, and b reaches, there's a typo here, this should be a y. So if X can reach A and next key of A is B and B reaches Y, then Y is reachable from X. And since reach is also reflexive, it will also handle the case that A reaches B. Okay, so let's see this in practice. So I have here the singly linked list. This is the code with the next key and head and elements. We have the specification, and here we can have the go state, and somewhere we have the hooks. And the hook for storing the next key is now a bit more complicated, because we not only need to update the ghost successor, so we not only update the ghost variable if we update the next key, but we also update the reachability predicate. And this is done with a have reach. This is a kind of syntax that you have to learn. And here is basically the same formula that we had before. I think this here is not really necessary. It's the same formula. And then we have some invariants that we need to prove. For example, that reach is reflexive. Everything can reach itself. If something comes before another element and the other element comes before X, then X must be equal to X, and so on. So these are the invariants that we prove, and then we can actually prove the full correctness of our function. So for example, we can check for insert that if the invariants held before, and we call reach, and we call insert after from key after key. Then first we can reach key from the head. So the key was really inserted in the list. And we can also prove that every other element, we call it here rando boy, that was in the list before is still in the list. So no elements get lost. And we have similar rules. So we also check when insert reverts and so on. We check that insert works if we insert at the head, which is encoded by using after key equals to 0, and that it works if we insert it somewhere else than the head. And all these rules we can check with our prover again. And I already did this, and all the invariants hold. So this is how we can express reachability. And I have to say it's still a bit tricky to come up with all the invariants. You have to figure out that you need this reachability predicate. You have to look up how to update it. And you then have to debug all the problems there. And there is also the problem that you need a lot of auxiliary invariants. This is the ugly detail that I skipped over. So I have this reach invariant, which is kind of nice. We have another invariant that basically states that the successor of key is the successor of key in the sense that it's reachable. So here's the definition of successor. It's reachable from key. It's not equal to key, and it's the first one reachable. So if there's another X in between A and B, then X must be equal to A or equal to B. And this way we can express, using the reachability predicate, the next pointer and recover it again. And this is also some important definition that you have to come up with, because otherwise the verification doesn't succeed. Okay, so this is basically what I wanted to tell you. So are there questions? Or do you want to see something like changing something in the code and see if the error is caught?
I have a question.
Yes.
Yeah, like I was wondering if I wanted to check, I wanted to write a rule like if I start anywhere, eventually I would reach to tail with a single linked list or a double linked list.
Yes.
So how would I approach to writing the same rule?
Yeah. I mean, there are two things to answer. So one is you can use the reach predicate. So if you want to say you want to say that something is reachable, you can express it in the spec by saying require reach of head, comma, then your element.
Okay.
And if you want to reason about the code, then it gets a bit more tricky, because if you have a code and you have, for example, a function that iterates the list, and you want to show that it iterates all reachable elements in the list. This would be an example that would be quite an interesting property. So if you have a code, then if you have a while loop that calls the next pointer each time, and then it calls some function on each element, then it should call the functions on all reachable elements. And this is something you can partly prove with the reachability. So you make a rule, you state in your rule something like so you make a rule, you require all your invariants, probably you require that reach had some element holds before, and then you do your call your function like list, and then you want to assert that maybe the iterate list sets a Boolean value, and you have a function where you can check was iterated. You can even do it by overriding one of the functions here. You could, if the iterate list calls one of the functions, you could replace it by a spec function, and in the spec function you set was iterated to true, and then you can check here if was iterated is true. So this is one way you can check that every reachable element was iterated. And it's kind of a trick, because we check it for every possible value of some element that fulfills this predicate. We check it for all elements.
Mm-hmm.
And there is one caveat here, because the iterate list probably uses a for loop. You have to give a max unroll depth. And if you and if the element is too deep into the max unroll depth, you have to use the optimistic loop assertion, and then it will not be a complete proof that this rule is correct. But it will basically, if you use 3 iterations, then you can be quite sure that it's correct.
Fine.
Does this answer your question?
Yeah. Thank you.
Any other questions?
Yeah, I have another question. I wonder how the update was working for your ghost variable. So you say there is a havoc there, but how are the new values becoming correct? Like, does the quantifier somehow is required correct?
This is a very special syntax. It's a havoc with an assuming. And this assuming predicate can talk about the old and the new state of reach. So it's like a havoc and an assume followed by an assume. And the assume will ensure that all the states that were written to reach will fulfill this property. But the important thing is you can even talk about the old state of reach. So you can read the old state of reach in this assuming predicate. And this is what we do here. So we havoc reach assuming the update successor, and the update successor uses the reach of old XY.
Mm-hmm.
And internally, this is translated, of course, to a formula. So so you have basically one variable for reach before this havoc and one variable for reach after this havoc. And then you have this quantified formula that basically you insert reach old for one of the variable and reach for the other, reach new for the other.
Awesome, thanks.
More questions?
So thank you very much, Jochen, and I want to emphasize that we will share the recording and also the spec will be in our example repository, and much of this can basically be copied. The EnumerableSet is a widely used contract, and so it can be very useful to start with these examples. So thanks for joining, everyone.
Yeah.
Thank you.
Thank you very much.
Great job, Jochen.
Thanks.
Thanks.